Maybe.
Here we go, recording.
Okay, so it is my pleasure to introduce Patricia Ning, who is virtually visiting us from University of Michigan at Ann Arbor. She finished her PhD in 2018 in University of California at Santa Barbara, and she will talk about high-dimensional parameter learning over general graphical state space models, beating the curse of dimensionality. So, please.
Thank you. I'm going to share my screen with you. Okay. Okay, can you see it? Yeah,
perfect.
Great. Okay, thank you so much for the introduction, and thank you so much for getting me here. I feel it's quite an honor to give such a talk in such a great department to all the excellent people as you are. And in this talk, I'm going to talk about the high dimensional parameter learning over the general graphic models. And so the reason we are doing some virtual interview right now is because of COVID. Since the year 2019, and we already have 328 million confirmed cases worldwide, and already more than 5.5 million deaths. So that is a very huge number, and this is a big crisis to everybody of Earth. And we can see the European Union is gets the highest number, and then just followed by our United States. It simply affected everybody's life nowadays. And we have a lot of data because for each place, for example, New York State, it has the daily data published with tested positive and total tested like that. So you can think with New York State and other places, we have a huge amount of data every day. There is two dimensions of the data. Firstly, the spatial dimension, many places. There is time dimension. The data is time dependent. So we have two dimensions involved. This kind of spatial temporal just means the spatial dimension and time dimension. This combined system. Disease transmission systems have this kind of properties. Firstly, it's high dimensional. It's two vertical and horizontal dimension, both. And this non-linear. And it's non-Gaussian. Gaussian means normal distribution, but here it's non-Gaussian, it's very general, and it's stochastic. There's noise involved in the mathematical modeling, and it's stochastic, not deterministic, and it's imperfectly observed. Or you can say it's partially observed because our data may not be accurate. That's the point. So based on some research published in Science journal, the spatial temporal inference for epidemiological and ecological systems is arguably the last remaining open problem from the 6 challenges in time series analysis of nonlinear systems. So it's very challenging, this problem with these properties. A disease transmission system is stochastic and imperfectly observable. Thus, it's commonly modeled by a state space model in the terminology of machine learning. In others, for example, in engineering and in mathematics, it's called Hayden-Markov model. In engineering, sometimes it's called a partially observed Markov decision model. This model is widely used, but here I'm going to consider is an extended state space model. With this model, as usual, we have the latent state. Latent state is we cannot observe it directly. It's a Markov chain taking value in a general Polish state space X. Polish state space is very general. You can think of it as like a separable Banach space. That means it incorporates discrete value, continuous value, real value, and complex value. So it's very general. And here I consider it equipped with a general reference measure psi. And my data point is it's called observation sequence, YN. This is a Markov chain. It's conditionally independent given my latent state, Markov chain X, and takes value in another general Polish state space Y. It can be the same, but in the general case, it is different. It can be different. And it has another general reference measure, all the same. But anyway, it's a very general situation. So here, why it calls it's extended state space model is because here I have another macro chain, theta n. Theta n here is added for the parameter learning purpose. It has its own state space and own measure. So here I'm considering the very general situation. Not only that, my transition dynamics is also very general. So I don't know anything about it, but I do know the transition is time inhomogeneous and it's very general. The f xn under xn minus 1. So to see it in this plot, we can see from the left to the right, you have the dynamics. It's evolving each day based on the yesterday. For example, today based on yesterday. This is called a Markov property. And here you can see theta has its own dynamics. And based on theta, I have my dynamics for x. And based on this x and theta, I have my dynamics for y. So this is a dependence structure. And my state for x n, y n, theta n, and each time point n is a random field. This random field is indexed by a large graph. Here I consider it a general graph with V standing for the set of vertices and E stands for the set of edges. I consider here there is a partition to this big graph. It's non-overlap block partition. So let's see this plot. For example, if I only have 8 vertices, I have the partition, 4 partition, this partition to participate to be 4 blocks. So the first one is 1, 2, vertex 1 and 2 in block 1, 3 and 4 in block 2, 5, 6 in block 3, and 7, 8 in block 8. So it's non-overlapping blocks. So mathematically describe it is like this. For example, if a key is a block and a key prime another block, if these two are not equal, not the same block, and there is no overlap, no interaction, no interpart, and the union of these non-overlapping blocks is my vertex set. I also suppose there is R neighborhood interaction. Let's see this picture, this plot. This plot gives you the 3 neighborhood interaction. So you can see it's in one step, xn given xn minus 1 time step. So for example, in the middle, my xni is only dependent on xn minus 1, I minus 1. I minus 1 means the location of the vertex denoted as I minus 1. And also it depends on xn minus 1, I. I is the location of the vertex. And also depend on the xn minus 1, I plus 1. The location is I plus 1. So it you can see it's 3 neighborhood interaction, 1 time step, R equal to 3 situation. So the mathematically describe it is, I have the R neighborhood and my dynamics, the probability transition function, xn v and the vertex v is under the xn. This dynamic, if my xn minus 1, the neighborhood of v is equal to the x bar n minus 1 neighborhood v. If these two are the same, they have the same dynamic. So this is a model setup and assumption. Why it makes sense? Because with a big graph, we always have a finite interaction in real life. Your interaction cannot be really large usually. So this is finite range interaction. The algorithm, particle filter algorithm, PF in short, is widely used in science in many areas. For example, engineering, epidemiology, biology. How this algorithm work? Let me firstly describe it in this flow chart. At the beginning, I initialize the model, initial value of my dynamic, and initialize the parameter. Then I have 1-step prediction by my X dynamic, the probability transition density. Then my data comes in. Based on my data, I just update my work, my prediction. And it's called a resampling. And for each time step, I do this way in a loop. So this has a recursive structure, recursive on each day. And the way why it works, you can think like in the biology, it's called evolutionary energy. So firstly, I have the mutation, then fitness, and then I have the natural selection. That is when the time your data comes in, you let the nature select what is the best prediction of your estimation, like that. This particle filter algorithm has a big issue. It's been mathematically proved it has a curse of dimensionality. The point is that, for example, on the day 100, my prediction for x 100 given my data point y1 to y100. This is my observation for 100. This conditional probability has the curse dimensionality. The reason people find that is, if I update my prediction by all the data points in the space, in the whole graph, it has a curse dimensionality because the algorithm error is exponential with the dimension of the graph. So people just think, if right now my error is exponential with the dimension of the graph, if I just updated my prediction by a block of the vertex, will my error to be just exponential with the dimension of this block? It will be much smaller. So this is a simple idea, and it has a block particle filter algorithm. So the prediction is the same, but when we update the data, update my estimation based on the new data, I partition my graph into different blocks, and each block only update my estimation based on the data in this block only. And then after that, I combine my estimation and go to the next step. So this is the block-wise particle filter algorithm. And it really worked. And mathematically proved it worked. I'll talk about that later. So my work based on the block particle filter algorithm is have more complicated structures here. Firstly, with this new Markov chain of parameters for parameter learning, firstly, I need to perturb my parameter. See, as time goes by, I have an iteration in here. It's the M for M iterations. After that, I hope to achieve some convergence of my parameter, the one I guessed. How it works here. Firstly, I have the model parameter initialization is the same. And then I treat my parameter as stochastic. It has some perturbation here. And then I predict my latent state and my parameter. After that, I go to the different blocks of the graph. Based on the data in each block, I update my state, update my parameter. After that, I combine all the block-wise estimation together and go to the next round. Firstly, it's recursive. And after all the recursion is done by each day, I do it in the loop again based on M. M is the iteration. So here, this algorithm is both recursive and iterative algorithm. The existing algorithm for this kind of parameter learning purpose in machine learning is two mainstream algorithms. First one is called iterative filtering algorithm. And it has the first version published and Proceedings of National Science Academy, PNAS in short, in 2006. And then later they improved their result. It's called version 2, IF2, also published there. This algorithm is called iterative filtering algorithm. It's based on the particle filtering. As we just mentioned, it has the curse of dimensionality, which means its performance goes down really fast as the model dimension increase. This work as a particle filtering algorithm. This is able to handle the highly nonlinear latent processes. That's a good part, but the bad part is it has a curse dimensionality. Another one published in Science last year, in 2020, it's called iterated ensemble common filter algorithm. Ensemble common filter is widely used in engineering and in other science. This algorithm it can be scalable to high dimensions. So the high dimension is fine. However, to the nonlinear, non-Gaussian problem, it's not fine. It's just ineffective. That's the problem. So let's talk about the block particle filter algorithm. We just mentioned that it works. This work published by Professor Van Handel in the Math Department and Princeton University, and his student Rabskini in Princeton. Right now, Rabskini is already a professor in Oxford. And this work published in 2015 and the Annal of Applied Probability. What this work is, it was not anticipated to be applicable to real high-dimensional problems. So it's just theoretical in nature. They mentioned it's just essentially a proof of concept. And it's also far from clear whether this simple algorithm is of immediate practical utility in the most complex real-world applications. However, the good part is they really provide a first rigorous analysis of a local particle filtering algorithm in high dimension. So this algorithm has the provable mathematical performance guarantee. It's a really big thing in the machine learning community because it has a math performance guarantee. As we know, most machine learning algorithms, for example, like in deep learning, it just works well, but people don't know to what extent it can work well, and in what kind of situations it works well. But this work by Professor Van Handel and Rabskini, they can show in some situations it works as long as it fits in some sufficient conditions. We can have the performance guarantee. They also showed that it's in fact possible, and at least in principle, to develop some algorithms whose approximation error is dimension-free. That's a big thing in machine learning. So before we go to the proofs, let's see the result of this my algorithm. Let's consider the measles analysis in England. So I consider 40 cities, ranked by the size of the city. Like if I rank number 1 of the city, which means London is the biggest, from the year 1915 to 1965. So that's the data looks like, the simulated data. So I use the SERR model in epidemiology. This is the most common model in epidemiology. So B here means it's birth. S means susceptible, which means for everybody of Earth, we are susceptible. And then I have the exposed. Exposed means I have the chance of already I interact with somebody already get, for example, measles. That means exposed. Then I have infected. People already got it and they recovered. So the worst situation is death here. So with this SEIR model on this big graph, each vertex has its own SEIR Markov chain model. And there is an interaction here. Why there is interaction? Firstly, with this Markov chain model, for each vertex, for example, V, the transition from S state to the E state is modeled as a negative binomial death process, according to some research published in the Annal of Applied Statistics and the stochastic process and its applications. And with the over dispersion parameter, sigma SEV, here, this stochastic model is for the better data fitting of my measles data. And the rate of this transition is given by this interacting particle system. Let's see why there is interaction. Here I have the alpha V, and here is another vertex V2. And you can see this coupled here, fully coupled. This vertex coupled with another vertex, and there is summation. So it's one interacting with all the rest, fully coupled in this situation. And after this highly nonlinear parameter, I have another one, R0V, which means for each vertex, I can estimate the annual average basic reproductive ratio. What this ratio means and why I need to model as each vertex base, each location base, because the transmission speed, for example, COVID, the transmission speed in New York and in Florida, that's very different because New York has a big population density, a lot of people there, and there's less people in Florida. So that's why people need to estimate each place differently. Okay. So let's see the performance analysis. If I learn the initial values for each location, so if I have 10 locations for these 4 initial values, that's 40 parameters to learn. And if I have 80, if I have 20 locations, that's 80 parameters to learn in total. So you can see with the ensemble common filter metric, all the algorithm works really well in this situation. And also in my block particle filter metric also works really well, even in the particle filter metric. So that means all 3 algorithms works in all of their metrics. The next case study is I add on R0 weight for each location weight. And in this case study, we can see it's the ensemble common filter metric. We can see the IF2, the algorithm based on the particle filter, is already not work as the dimension goes high. And also in my block particle filter metric, it's also not go work. And in the particle filter metric, also the kind of a similar situation. But here the particle filter metric, I just mentioned, it has a curse dimensionality. So it's not a reliable metric. So I just increased the difficulty in the parameter learning. I want to learn a highly nonlinear parameter alpha weight. So in this situation, we can see the INTF algorithm, it performs really bad. Actually, here, because it performs really bad, it just feels like the IF2 not so bad, but actually it's really bad just because the INTF is worse here. So you can see only the IBPF works in all these parameters, all these metrics. Next, I consider the hardest situation that I learn all the parameters for each location, for 7 parameters for each location. And we can see that the INTF just disappeared because it totally does not work. And the IF2 is the purple one. It's just the performance goes down really fast. And the IBPF works in all the time and in all these 3 metrics. And it's even better than the true parameter. True parameter is the black colored one. It always outperforms the true parameter. How it can be? Is this too good to be true? Because it can even outperform the true parameter. The situation is that with the high dimensional optimization problem, the true parameter may not be the optimizer. But this IBPF algorithm can find the optimizer in this case. That's why it outperforms even the true parameter. So let's see the theoretical performance guarantee. The very thing that differentiates us to the computer scientists because we can give the theoretical performance guarantee here. We firstly consider the true joint parameter, nonlinear filter. It is defined by this way by a conditional probability, my estimate of xn, theta n, given all the data points up to n, y1 to yn. And this dynamic involves as follows. It's a recursive way. Firstly, I define my predictor. So this is, I use the operator theory in mathematics. Next one, given my data comes in, I have the correction operator. So there is 2 operators here, prediction and correction based on data. And the algorithm IBPF approximated the nonlinear filter involved and below. So firstly, I denote as the pi n minus 1 hat. I have the prediction, my sampling. Sampling has its own sampling operator defined in this case. And I have my block correction. But I feel this problem is too hard to handle. Then I introduced an intermediate joint nonlinear filter tied to the N. The difference here is I introduce I block operator here. That means I partition my graph and also my partition my conditional probability here. Here, there's no sampling, just the partition. So this is also a theoretical nonlinear filter, no sampling, no stochastic algorithm involved, just math. So I have the prediction block correction. Okay, I introduce an intermediate step. With this localized algorithm, I also need the localized version of metric. So I define my distance of the metric of the two probability measures. This metric is, I worked on its ZK, it's a class for measurable functions such that if in block K, the value is the same, the function value is also the same. Okay, so this is a localized version of the metric. So you can think if here is no expectation and no localized, so this is simply the total variation distance in mathematics. Okay, but here is a localized version. And I also need the localized version of the standard mixing assumptions. With the particle filter algorithm, I have the global mixing assumption. This assumption is the transition density is lower and upper two-sided bounded. This is to make sure my algorithm has ergodicity property. For that, it will converge. And the result, theoretical performance analysis. So under this localized version of the standard mixing assumptions, I give some sufficient conditions. If the lower bound of the X dynamic and the theta dynamic is bigger than this quantity for each N, so uniformly in time, and for the block K is in the partition. With this local metric, I can bound the approximation error, the algorithm error here. Algorithm error, because I introduced this intermediate filter here, I can just consider two. It's like a triangle inequality in mathematics. The first is caused by the bias introduced by the graph partition. The next error is just from the intermediate filter and the algorithm filter caused by the stochastic sampling. I have this error bound uniformly in time. And we can see here, the first one is shows there is exponential with the dimension. Here is from in one block to its the boundary of the block. And the next one is just a sampling error. To prove this error bound, here we can see the result is already, everything is just in localized, no global involved. There's no global dimension here. Just you can see it's the cardinality of the block K, not the cardinality of the matrix here. So already have realized the curve. Here I can beat the curve dimensionality because there's no cardinality of the graph anymore. Just the cardinality of a block here. To prove that, I have used two techniques. First technique is called decay of correlation property. This property arises in stochastic physics. And in regard to the investigation of high dimensional networks, and based on some of my work published in this area, for example, Journal of Statistical Physics and its semi-discrete mathematics. But the difficulty is here, even my model has the decay of correlation property. I need to show the conditional probability inherent from the model on this property. In this setting, it means that the effect on the distribution in the block K of a perturbation made in another block K prime, it decays rapidly in the distance of these two blocks, based on which we can define the neighborhood of one block, like that. And I use the theorem, it's called the Dubrashin comparison theorem. This theorem means, for example, if I have the perturbation made and vertex I want to check how it affects vertex J in this case. I use the rho xi to denote as that. Another quantity is why I'm working on this D. There is a D here. D is the summation of all the n, time point n, and power of C here. The reason I'm doing that is, for example, vertex I can affect vertex K, and the K can affect G. Not directly I affect G, but here is accumulated indirect effect, influence here. I want to measure that. And the BJ is I want to see the difference between two measures, probability measures. So if I can bound, it's like here, this upper bound to accumulate all these affections, influence here. I can bound it here. I can show it I can establish the decay correlation property in this setting. This is the tool I use mathematically. And I use that to control the bias. But however, for the variance, the technique is different. The technique is called a computation tree. The reason is that if I consider with the true parameter, I have a conditional probability to work on. However, my intermediate filtering, this is not just a conditional probability. It's defined recursively, algorithmically. It's not a conditional probability anymore. So the technique here, I still want to do what I can do with that theorem. I need it to become a conditional probability. How can I do that? Remember here we have for example, 3 neighborhood interaction. Here I just make each one duplicate. For example, here I have the E, D, and C. I just replicate. And I want each one like to stand up and make some replications of itself. In this way, I want to handle the interaction. So after this kind of replication, I built up a tree network. It's called a computational tree technique in analogy to the belief propagation algorithm in machine learning. This technique is developed by Rabsky and Van Handel in their paper. Based on this technique, I can make it to be a large Markov random field, and then from that to contribute to construction the conditional probability. So mathematically put, with this work, I just have each operators based on its parent block interactions. So here is block-wise. You can see NQ1, which means the neighborhood of the blocks interact with my block Q1. So I can trace back. You can see this is a huge tree, and each one has its parent blocks interactions based on this product and my block-wise operators to contribute like that in the proofs. So based on these two techniques, I can bind my algorithm error. So my future work based on this, I already described the mathematical performance guarantee and the numerical analysis performance. And in this work, actually with each partition, I use just a trivial partition. I just allow each block have 2 vertex. The reason I do that is I want to compete with other algorithms, and I do not want them to feel, I just use the best partition for my algorithm. I give myself some advantage just to show I can, for the fair performance comparison with other algorithms. Actually, in the next step in my research is I want to know what is the optimal partition, this kind of learning. And I want to give some guidelines to the user of this algorithm, how they can mathematically find their best partition of the algorithm. So one way I'm thinking about this direction is based on some works by Eknor Mosel and Joe Niemann and Alan Sly. Mosel is a math professor at MIT. Joe Niemann is a math professor at UT Austin. And Alan Sly is a math professor at Princeton. There are some work published in the Annals of Applied Probability, and there later work published in the Combinatorica. They showed that if the reconstruction problem, the Casten-Stegon bond, the reconstruction bond is non-tight. There is an information theoretically solvable but a computational hard region, phase transition region of the corresponding clustering problem of the stochastic block model will appear. So that's the connection. And when they do the clustering problem, they handle that is by the reconstruction technique. So I have a serious work published in this area on that. So this is something I want to do in the future in methodology, in machine learning, in mathematical machine learning. Another research I want to do in the future is about the theoretical analysis. I just mentioned the research in high dimensional, but what about the infinite dimensional? In math, a trend in mathematics is we want to handle the situation in infinite dimension. So let's think about this stochastic control and stochastic optimization problem. So here I have my running cost function as a g function. It depends on the time s, and it's the path of my stochastic process. I have a multi-dimensional stochastic process x. It's path dependent. Xs means the value from the time 0 to time s. And I have a coupled, it's a coupled y process. It depends on the path of x. And I have my control process. Control process is in the admissible set AT. I want to optimize on this control. And I have the terminal function H, terminal cost. It also is path dependent. Here, the path of the stochastic process lies in the infinite dimensional functional space on 0 to t, capital T, finite time horizon, and taking values in RD1. So there's an infinite functional space. And my function, my optimizing function, VTXT, is also time dependent in this case. So this is my work in the stochastic control with infinite dimension. And another one I'm working on is future research. It's a collaboration with the scientists. So I just mentioned that there are two competing algorithms. The first one is Yin-Zimbo common filter. When they applied to COVID, their work published in Science. And the iterated filtering algorithm, the first one applied to the cholera data. Cholera is the epidemiology kind of disease. It's published in Nature by my co-author and his co-author Posco. Is Professor Mercedes Posco in University of Chicago Department of Epidemiology and Ecology, published in Nature. And later they used the IF2 algorithm published and used apply on COVID, published and PNAS. Currently, I'm using my algorithm in collaboration with them, with the scientists on the COVID data. This work is going to be done soon, and we already have some kind of the very interesting scientific findings. So this is for the disease prevention and control. We want to stop the coronavirus, and then we can meet in person. And my algorithm is quite general, not limited to the COVID or measles. It can also apply to the cholera, dengue, and other transmission disease, and also other areas, for example, finance, and in other areas, as long as there is an interacting particle system, and also is a stochastic, nonlinear, partially observed. It's all applicable. Okay, so that's the things are already done, and I'm going to do in the future. That's all I'm going to talk. The later is just a reference. And thank you for this talk. Happy New Year, everybody. And I welcome all kinds of collaborations. Thank you.
Thank you. Are there any questions? I was wondering if you could, somebody has a question? No. I was wondering, so what are the practical uses. So you said that you have some applications to COVID or potentially do some other things. Can you somehow give us a peek into what are the things that you can obtain?
Yes, in my work is quite general and theoretical, and I collaborate with the scientists on these applications with their expertise on real data. And currently we apply to the COVID, and later after this, there may be other cholera or dengue, and also finance applications, or maybe other areas. So as long as there is Markov chain and it's highly nonlinear interacting and non-Gaussian stochastic, they all fit in this algorithm. So it's quite general and widely applicable.
Any further questions? It's a lot harder to see what everybody is thinking when you're not in the classroom with everyone. Well, if not, then we will thank Patricia again.
Thank you all for having me here.
Thank you. I wish that we had the tea and that we have some really nice pastries before the colloquium usually. Hopefully sometime soon.